Let's consider this function, y equals x squared plus 6x minus 4. So there's a bit of an issue if you just start picking a bunch of random x values to get y values in ordered pairs. You might not get the whole parabola, and it might take you a lot longer too. If you say x equals 1, so 1 squared plus 6 times 1 minus 4, 7 minus 4 equals 3, and you start going through, you want to be sure you get the actual shape of the parabola, and that might take a little while. Here's the parabola for y equals x squared plus 6x minus 4. And I hope you notice that if we started, and at the beginning, if we knew the vertex, we could then pick a couple ordered pairs on either side and reflect them and have a much easier time graphing this, rather than just picking a bunch of values. And like if we pick 1, 2, 3, 4, we're going to be way off the paper. So if we know where we can start, how to get that vertex, then graphing becomes a lot easier for us. Turns out that there's a simple way to find the axis of symmetry. Each of these terms in the quadratic function are considered A, B, and C. So let's write down the values. Since the coefficient of x squared is 1, we don't write it, but it's 1, a equals 1. The coefficient of the linear term, 6x, is 6, and the constant is negative 4. What we are going to use is a formula to get the axis of symmetry. The axis of symmetry is found with this simple equation, x equals negative b over 2a. Let's try it with these values. B is 6, so negative 6 over 2 times a is 1. Negative 6 over 2, and that gives us negative 3. So the axis of symmetry is the line x equals negative 3. Well, look at what we have on the graph. That's our line, x equals negative 3. So if we use x equals negative b over 2a, we can get the axis of symmetry right at the beginning. Now the axis of symmetry is incredibly important because notice the vertex is always on the axis of symmetry. Since the vertex is on the axis of symmetry, we know the x value of the vertex. If we know the x value of the vertex, we can put it into the equation and find the y value of the vertex. Let's try that.
Y equals negative 3 squared plus 6 times negative 3 minus 4. And you realize I already did this in the table of values, but we'll run through it one more time. There it is. The y value of the vertex is negative 13.
That gives us the vertex at negative 3, negative 13. Now we know, let's just start finding some values to the left or the right and then reflect them. If I find the values here at negative 2, negative 1, and 0, I can then reflect them on the other side. The y-intercept here is 0, negative 4. If x is 0, those two terms zero out. 0 squared is 0, 6 times 0 is 0, leaving us with negative 4. Interesting. C is negative 4. I wonder how that bears out with the other ones we looked at. Here's an earlier one we graphed. When x is 0, y is negative 1. The c value is negative 1. So it turns out that directly from our equation, we automatically know something else about the graph. The y-intercept is C. There's another little tip that'll make graphing parabolas a lot easier. We're going to take another look at this parent graph to understand a little bit about the relationships of the points on the parabola. That's 0, 0. Here's 1, 1. So as our x value goes up by 1, our y value is going up by 1. If we go another unit to the right, we're going up 3. If we go another unit to the right, we're going up 5. If we go another unit to the right, we're going up 7. We would then go over again and up 9, then 11, then 13, then 15. The difference of consecutive square numbers are the odd numbers. We just keep increasing by the odd numbers. So over 1, up 1, over 1, up 3, over 1, up 5, over 1, up 7. Same thing in the other direction. Back 1, up 1, back another 1, up 3, back 1, up 5, back 1, up 7, back 1, up 9, and we can keep going like that. This is one we just graphed. Over 1, up 1, over 1, up 3, over 1, up 5, over 1, up 7, over 1, up 9. So if we have the same shape as the parent graph, at least the integer ordered pairs, over 1, up 1, over 1, up 3, over 1, up 5, and we follow that pattern up both sides of the parabola. This is not going to work quite the same way if the a value is not 1. And we're going to take a look at a couple quick examples of what happens if a is not 1. Here is a quadratic function where the value of a is not 1. We're going to approach graphing this the same way we've graphed the other ones. Find the values of a, b, and c, find the axis of symmetry, use that to get the vertex, and then we'll find some ordered pairs for the graph. We have a equals 2, b equals -4, and c equals -1. The axis of symmetry is found with the equation x equals -b over 2a. Negative b, that's -4 over 2 times 2. -4 is +4, 2 times 2 is 4, 4 over 4 is 1. X equals 1. That is the axis of symmetry. I'm just going to go ahead and draw that on here, just so I can get an idea of where this thing is on the coordinate plane. That's the axis of symmetry, x equals 1. I will use the value of 1 to find the vertex, the y value of the vertex. Y equals 2 times 1 squared minus 4 times 1 minus 1. 2 times 1 minus 4 minus 1. 2 minus 4 is -2 minus 1, -3. So the vertex is at 1, -3. 1, -3. I know another ordered pair automatically. I know the y-intercept. The y-intercept is the c value. C is -1. So my y-intercept here is -1. Well, if I get a couple more values to the left and ordered pairs that way, I can just reflect them. So let me try x equals -1 and x equals -2, see how those work out for a couple more ordered pairs. If x equals -1, y equals 2 times -1 squared minus 4 times -1 minus 1. Be careful that you put the -1 in parentheses, square that number first, then multiply it by 2. The order of operations tells us to take care of exponents first, then multiplication. So I have 2 times 1, and that gives me +4 minus 1. 6 minus 1 is 5. So I have an ordered pair here, -1, 5. And let's try x equals -2. Y equals 2 times negative 2 squared minus 4 times negative 2 minus 1. 2 times 4 plus 8 minus 1. 8 plus 8 minus 1, that's 15. So I have another ordered pair at negative 2, comma 15. Let's go to the graph, put these on here. Negative 1, comma 5. 1, 2, 3, 4, 5. And negative 2, comma 15. I don't know if that'll fit. Yeah, it's good. It's right there. Since I have the axis of symmetry, and I have ordered pairs on one side, I can go the same distance on the other side to reflect those points. This is 1 unit to the left, so I can go 1 unit to the right. This is 2 units to the left, I can go 2 units to the right. So with 3 units to the left, and I can go 3 units to the right. And that gives me this parabola. And you're probably noticing this is a little bit different than the previous ones. In fact, if we compare it to this parent graph that I drew a few minutes ago, you see how this one is a little bit narrower? Sometimes a parabola is narrower, and that is a result of this value of a, which is making the parabola narrower, because we're multiplying this first term, and so our output values are increasing. So instead of over 1 up 1, over 1 up 3, I'm going over 1 up 2, over 1 up 6. I'm doubling those output values. We have one more example to take a look at, so we'll have a complete view of what can happen with different a, b, and c values when we're graphing a quadratic function. Here, a is negative 1/2, b is 2, c is 1. Same start. A equals b equals c equals. Then we go to axis of symmetry. X equals negative b over 2a. Now b is 2, so negative 2 over 2 times negative 1/2. Well, negative 2, 2 times negative 1/2 is negative 1. Negative 2 divided by negative 1 is 2. So x equals 2 is the axis of symmetry. We're going to use that value in the original equation to find the y value for the vertex. Y equals negative 1/2 times 2 squared plus 2 times 2 plus 1. Negative 1/2 times 4 plus 4 plus 1. Negative 1/2 times 4 is negative 2 plus 4 plus 1. That ends up with 3. So y equals 3 when x is 2, so the vertex is 2, comma 3. Let's move to the graph and just get this information on there to make things a little bit easier. So x equals 2. The axis of symmetry is over here. X equals 2. The vertex, 2, comma 3. 2 and 2, 3 is right there. Now we can do a table of values to find out a few more ordered pairs. Well, let's see. I have 1, comma 2.5, negative 1, comma 1.5. Don't forget we have the y-intercept. Let's get these things on this graph. 1, comma 2.5. Right in between here. 0, comma 1, because that's my intercept. Negative 1, comma, negative 1.5. Negative 1, comma negative 1.5. Right there. If we reflect these, well, down half a unit and over 1. Here this is 2 units over. And then here, 3 units over when I'm at a y value of negative 1.5. There we go. It's looking a little bit different than the parent graph. Again, it's looking like it's a little bit squished. It's a shrink. We call this a shrink. We call the narrow one a stretch. We call this one a shrink. You'll also notice it opens upside down. That's a result of the negative for the a value. So if the a value is negative, the parabola will open upside down. If the a value has an absolute value between 0 and 1, we're going to have a wider parabola with a shrink, as opposed to this one where the a value had an absolute value bigger than 1, we had a stretch, a narrower parabola. A narrower parabola when a had an absolute value bigger than 1. When a has an absolute value smaller than 1, it is a wider parabola. And the negative reflects it. That is how you graph a parabola when you have a quadratic function in standard form.